also weird.
Good morning, everybody. Welcome back to our final day of Galois theory. I know, it's tragic. I am good. I am really good at this class. This has been a very goofy class. Plan for today is honestly not that much. Got a couple small things I want to talk about, and then see what questions and such you all have, or if there's anything you all want to talk about. We're going to talk briefly about insolvability of degree 6+ equations. So last time we showed that we found an example of a degree 5 polynomial that you can't solve by radicals. Solve. And then we're going to generalize that to degree 6+.
Can we just multiply by any polynomial that's like degree 1 or whatever?
You can, but we're going to find a whole class of polynomials we're going to generalize and talk about a whole class of polynomials to degree 6+ for which you can't do that. You have these.
Thank you.
Okay. Hey Lydia, come pick up your homework. Then finally, a formal statement of the fundamental theorem of Galois theory, which we've kind of already said informally when we went through that example in class. But just for funsies, take a look at it. Yeah. Got my usual office hours this afternoon, 1 to 2. Tomorrow, 11 to noon, 1 to 2. Thursday, 1 to 2. And your all's final. It is out. It is up. It is fun, ? And it is due on Monday. Yes, even for you, man. Even your final.
Did anyone end up giving you questions or not?
Questions? Oh, no.
I forgot about it.
I didn't realize that came out fast. That was like 5 hours after you were like, oh, you can give out questions and just like all.
It was literally the next day. Wow. 5 hours.
In terms of in your office time, I feel like.
Oh, sure.
Yeah.
I mean, hey, if you'd emailed it to me, if anybody had given me questions for us now, I would have given you one. Any other questions or comments before we get started for today?
I don't need.
Why is Euclid so good at dancing? Because he had algorithm.
I was sure it had something to do with algorithm.
Yep. Alrighty, and with that, pick things up where we left off last time. So last time we showed that f of x is solvable by radicals if and only if your Galois group of f of x over whatever your base field happens to be forms a solvable group. And we use that to prove that the quitic is generally insolvable because there exists degree 5 polynomials over Q, where if you take the Galois group, you get S5, and as we've seen, S5 is not a solvable group. You can't form this nice sequence of normal subgroups leading up to, from the trivial group up to S5 that results in abelian quotients. So, first thing I want to do today, talk about how do we generalize this degree 6 or higher. And first of all, y'all know linear independence from linear algebra? We're going to go beyond that today. We're going to talk about algebraic independence of a set of elements.
That's really great.
Which, think of linear independence as being, independent over lines. Algebraically independence is like polynomial independence in general. So, here's the scoop. We're going to let L over K be a good extension. For the result we're going to have here in a second, we're going to let K be a field of characteristic 0. And we're going to say that a set of elements, K1 through AN, as a subset of L, is algebraically independent over K if for all polynomials f of x1 through xn in K, f of a sub 1, a sub n is equal to 0 if and only if f is the 0 polynomial. So in other words, the only way you can take a polynomial, plug, and this is a polynomial potentially in many different variables. The only way you can take a polynomial, plug in all of your algebraically independent elements, and have that polynomial evaluate to 0 is if that polynomial is literally just the 0 polynomial that maps everything to 0. So what would be an example of that?
What does it mean? Is that just multiple inputs into the polynomial?
So let's look at a non-example first. Let's let a base field be Q, and let's let our set of elements, and give it a name, S. Let's let S consist of 1 square root of 2 square root of 3. Question: is this a linearly independent set? Yeah. There's no linear equation that you could plug these numbers in for and gets 0. And get 0 except for 0 times 1 plus 0 times square root of 2 plus 0 times square root of 3. So we can say, if we have some equation of the form a1, if a1 times 1 plus a2 times square root of 2 plus a3 times square root of 3 is equal to 0, that tells us a1 equals a2 equals a3 equals 0, and that's enough to tell us we have a linearly independent set. However, this may be a linearly independent set, but I claim it's an algebraically dependent set. So what would be an example of a polynomial in terms of 3 variables? Like let's say x1, x2, x3. That if we plugged in 1 for x1, square root of 2 for x2, and square root of 3 for x3, what would be a polynomial in these variables that could give us a non-trivial polynomial that could give us 0?
x1 minus 1 plus x2 squared minus 2 plus x3 squared minus 3.
Say that again?
x1 minus 1 plus x2 squared minus 2 plus x3 squared minus 3.
Well,
we
that
could
would
make it all
certainly do
minus
it.
6, but it was that way in my head to keep it all ordered.
That would certainly do it.
You could also do, I think, x1 plus x, plus x1. It's like x2 squared minus x3 squared.
Or that too.
Say it again, Parker.
Yeah, shame, stop talking. x1 plus x2 squared minus x3 squared should do it as well.
Yeah. These are non-trivial polynomials over x1, x2, and x3, meaning the coefficients are not all just 0. But this set of elements as a root. So if we were to plug in f of 1 square root of 2 square root of 3, or g of 1 square root of 2 square root of 3 in that order, we get 0. So I would say that over Q, S is an algebraically dependent set. So what would be, yes?
I would think totally finding algebraically independent sets is going to be difficult.
Not that hard. You might think of an example of a algebraically independent set. It's harder than finding a linearly independent set.
Yeah.
But I don't think it's that terrifying. Jonah?
Would pi be, or be, I mean, the set containing pi be an algebraic?
That was where my head went also.
Sure.
Oh,
Let me ask you this, would any one element set be an algebraically independent set?
No,
not
Yeah.
if it's in Q.
Why not?
Why not?
well, 0, if that contains
that's not even linearly independent, let alone algebraically independent. Any non-trivial, alright, fine, exclude 0. Does any one element set necessarily give you an algebraically independent set?
Yes.
Andrew?
Not if it's algebraic over Q.
Not if it's algebraic over Q. Yeah, because you could take like square root of 2 for instance and say, oh, that's a root of x squared minus 2. That's a non-trivial polynomial that has this as a root. Just a polynomial in terms of one variable, it turns out. And so this would be an example of an algebraically independent set. Whereas this would actually be an algebraically dependent set.
So it's easy when we have transcendental numbers.
Sure. Yeah, you kind of got to have transcendental numbers. If you only have algebraic numbers, then you're always going to be able to do something similar, akin to what like Emily Rose did in her example. Just you have your A1, A2, A3. Just find minimal polynomials for all of them and literally just add them together.
So you could just have a bunch of algebraic numbers, but as soon as you add a transcendental, it becomes independent.
Well, not necessarily. You could have like multiple. For instance, if I were to give you this set, would that set be algebraically dependent or independent?
Just kind of grody.
This would be dependent
I see.
because just take x1 squared minus x2. That is pi, comma pi squared as a root.
What about pi to the pi?
I don't know. You tell me.
So am I allowed, if we have pi comma pi to the pi, am I allowed to raise one of my x's to the pi
No.
power?
No.
Because it has to be a polynomial, and if you're taking polynomials, you can't have non-natural number powers.
No, pi to the pi is
Now see,
with pi
With zero.
is algebraic.
so is there such thing as an exponential independence?
Yeah.
Oh, okay.
I've never really done anything with exponential independence, but you could certainly define that and do something
That's
like
not
that.
defined.
What was the function for just the square root of 2?
Natural numbers.
That is a polynomial in
Yep.
Q for which square root of 2, a non-trivial polynomial in Q for which square root of 2 is a root.
It doesn't have roots in Q or not.
Yeah, something to keep in mind is that your polynomials have to live in K, meaning all the coefficients of your polynomial have to be coming from K itself.
Would this be easier if we didn't have a characteristic 0?
Easier in what way?
Like there are
Finding more algebraically independent things?
Yeah.
Well, if you have characteristic non-zero, that means you have fewer polynomials to work with.
Yeah.
So yeah, I would say so.
So do you ever count them?
I can't count those ones though.
Only the
Yeah. So I said characteristic 0. Like you could certainly do this over fields of any characteristic, but the next theorem is only going to work for characteristic 0. Or if we look at our next theorem, we're going to say we're going to let characteristic of k be 0 and n greater than or equal to 5. And we're going to let S1 through Sn be algebraically independent elements over K.
How do we know they're SN?
How do we know there's what?
How do we know that they're SN independent elements? Like what is
Sn is that they're n independent linear?
Yeah, and independent.
We don't.
Elements.
We're saying if this happened to be the case.
Okay.
Oh, that's greater than equal to 5. So that's
Yeah.
Yeah.
Suppose you happen to have a set of 5 or of n linearly independent elements. If you can't find that many, then this This theorem just doesn't tell you anything.
Okay.
Then, we can define a polynomial, x to the n minus s1 x to the n minus 1 plus s2 x to the n minus 2 minus plus negative 1 to the n, s of n by itself is not solvable by radicals.
That's pretty hard.
No, it's not.
Well, wait, that's pretty hard.
Exactly. Yes.
So when we talk about insolvability of the quintic, are we talking about like
There exist quintic polynomials that you cannot solve by radicals.
over the rationals or over the reals?
Over the rationals.
Because this is not going to be a rational polynomial, right?
No. Well, assuming k equals q, you mean?
We're sure, right?
Yeah, because if it was a rational, because if this was a polynomial, yeah, well, I see. Yeah, so this is I see what you're getting at. Yeah, this polynomial lives in R.
Right. Okay.
Yeah, but this gives you a polynomial over R.
Okay.
Or wherever your S1, S2 happen to live, maybe.
Okay.
Etc. Turns out you can construct a polynomial over some whatever field L happens to contain your algebraically independent set, and this will give you a non-solvable polynomial over that field.
Wait, how would it be R?
These can't be in Q. Andrew, why can't these be in Q?
If they were in Q, then they
Or K if we want to.
Right. If they were in K, then they would be linearly dependent. So definitely algebraically.
Yeah, you can't have a set of like 5 or more algebraically independent elements coming from your base field. It's very easy if these are in K to construct a polynomial in K that has these as a root. For instance, f of x1 through xn equals x1 plus xn minus s1 minus sn would certainly give you a polynomial in K for which that's a root. So these need to not be in K in order to be able to potentially have algebraic independence in the first place. We're not going to prove this here. I'm too lazy. If y'all want to prove it, go for it. What I will say is S1 through Sn. Why do you think I chose S? And not just and no, the answer is not just because the book used S.
Because you wanted to confuse us by making us think of the symmetric group.
Haha, you've been confused. Nope. Although S does refer to symmetric. No, it actually is symmetric. Symmetric polynomials come into play here.
What? What are those?
What's a symmetric polynomial?
A polynomial that's symmetric.
Indeed. Glad we established that.
Meaning you can write it backwards and forwards and everything?
Palindrome. Well,
That's a palindrome.
That's a polynomial.
It's where, wait,
Palindromial.
oh, would you usually talk about polynomials in multiple variables being selected?
You do.
So
Yeah.
it's where like you could swap any variables.
Yeah, it's basically where a polynomial where if you swap around your variables, it comes out to the same thing.
So it's an even polynomial?
No, not necessarily, because usually you're talking about polynomials in more than one variable, as Andrew mentioned. A symmetric polynomial would be something like this.
What makes
It's symmetric because if you swapped x1 and x2 around, the polynomial would still come out to the same thing.
So it's really just.
So like f of a comma b is always the same as f of b comma a.
Oh, like this would.
Yeah, turns out there's a lot of cool properties of symmetric polynomials that come into play in actually proving this. And what ends up happening is you can show that f of x, in this case, has a Galois group of SP, symmetric group on p elements. And what do we know about SP? Sorry, not SP, Sn. And what do we know about the solvability of the group Sn?
Not over
It's
five.
not,
Because
as long as n is greater than or equal to 5. using properties of symmetric polynomials and playing around with this expression quite a bit, and eventually you get a Galois group that's equal to Sn. You show that any of the that there's automorphisms mapping any of the roots of this to any of the other roots, which means the Galois group is all of Sn, which means your Galois group is not solvable, which means the polynomial is not solvable by radicals.
Do you have to be able to switch around any two in a symmetric group? Or in the symmetric polynomial? Do you have to be able to switch any two variables?
Yeah.
So it's just a polynomial of one variable added to itself with different variables?
Well, you could also have like multiplicative stuff going on, like that would be another one.
Or x1 over x2 plus x2 over x1.
Yeah.
Assuming they're not zero.
Well, that's not polynomial, so gotta be
Oh,
careful.
Right. Forgot about
That is that would be symmetric though.
Yes.
Assuming they're 0.
What this gives us though is kind of a nice way to generate polynomials that are not going to be solvable by radicals. And it turns out over R you can show that you can do this for any n greater than or equal to 5. For any n greater than or equal to 5, you can always find a set of that many algebraically independent elements over, say, R, which tells us that over R at least, not only is the quintic not solvable by radicals, degree 6, 7, etc. are as well. And yes, Jonah, that's not the easiest way to prove that. But it gives us a way to sort of generate a whole bunch of them.
Annoying the complex numbers are kind of useless in this situation
Why are the complex numbers useless in this situation?
because they're not going to be algebraically independent.
Yeah, complex. Yeah, good luck finding algebraically independent sets of complex numbers. If your base field is C. Either questions or comments? All right, final packet time, and it's only one page.
Whoa, but then it's not a packet, it's just.
That's a short packet.
There's something on the front side, but not the back side.
Yeah, so it's.
I mean, in my notes, there's something on the back side of it.
Oh,
There's a
did you
lot.
get did you get the special edition?
I did not hear any of that, Jonah.
Have you ever talked about leaving students the empty packet?
The empty packet? Ooh. No, I haven't. That sounds like fun, though.
That sounds like something you should do like on one day of abstract.
No,
Maybe
empty
real
sets.
Yeah,
It's
it's
good
empty.
math, nothing.
Have the empty packet. And then, all right, but then all right, I'll do that real analysis. It's like, all right, here's the empty packet. Now here's a packet containing the empty packet. Are these the same packets?
All of these could be encoded in empty packets.
Yeah, you really want to. Yeah, but yeah, here's the fundamental theorem of Galois theory. Pretty much everything we discussed already. We're assuming we have a Galois extension, L over K. Lincoln, remind me, what's a Galois extension?
Sorry, I'm linking.
I thought you were Lincoln.
See, I almost made the same joke, but I restrained myself.
I didn't.
Okay, yeah, okay, Emily Rose, since you can't contain yourself.
Normal and separable.
Yeah, it's a normal. It's an extension that's normal, meaning it's a splitting field for some polynomial in K, and it's separable, meaning everything in L. Minimal polynomials and everything in L over K, there's no repeat roots. So suppose you have a Galois extension, then you can form this nice one-to-one correspondence psi between the subgroups of your Galois group and intermediate subfields between K and L that maps each subgroup to its fixed field. Where you may recall the fixed field of some subgroup of your Galois group, some set of automorphisms, is just going to be all your elements in L in your, say, your splitting field that are fixed by every single automorphism in that subgroup. And then just kind of a few general properties. H is a subgroup of B in the Galois group if and only if the splitting field of L contains the fixed field of H contains the fixed field of B. The number of elements in H is equal to the index of L over the fixed field of H and L. Number 3 just gives us kind of this formula. And number 4 is the one that says something about normal subgroups, that an extension is normal if and only if its corresponding subgroup happens to also be normal.
What does the superscript H mean?
Fixed field of H.
H doesn't have to be a proper subgroup, right?
And-
It just be any subgroup.
Yeah, H could be any subgroup. H could be the whole group. Yeah, in which case the fixed, yeah, and if H is the whole group, then the fixed field is just going to be your base
So it's
field.
the power set of Galois. Right?
It's the power. Well, no, because it's the set of all subgroups of the Galois group, not the set of all subsets.
Yeah,
Call it the power group, if you will.
power.
Which, no, as far as I know, is not actually a thing.
It could be that.
Sure, if you want to, like the set of all subgroups of the thing. Sure, if you want. I've never heard that described before. You can't just take all subsets though, because a lot of them aren't going to be subgroups necessarily. Andrew.
Number 2, if we plug that formula for the size of H into number 3, then don't we get that the size of the Galois group is just the size of the extension from L to K?
We do.
I thought that wasn't always the case.
Oh yeah. Give me a counter example.
Did we say,
You're right. It's not always the case,
but it will always be the case for Galois extensions?
but it's always the case for Galois extensions. And that's part of that's kind of part of the build up to this proof.
Okay.
To the proof of this theorem, is you end up showing that for a Galois extension that the formula you just mentioned, Andrew, does hold, that the size of the Galois group is equal to the degree of the extension L over K. Doesn't hold true for non-Galois extensions, which is part of why the Galois extension, why it needs to be Galois, comes into play. And hey, we even get this nice little quotient group isomorphism if you're looking at normal subgroups of G versus normal extensions of K. Number 4. There you go. It's Galois correspondence. That is the fundamental theorem of Galois theory. Theorem that you all used even without me having stated it formally in homework 7. That kind of tells us something about how do you find intermediate subfields for using properties from. Any questions, comments, or concerns? So what else can you do with Galois theory other than insolvability of the quintic? If we'd had another week or so, I probably would have spent more time going into detail on like looking at these classic constructability problems, like can you trisect an angle? Can you square a circle? Can you double a cube? Turns out you can use some Galois theory to say none of these are possible. Why? Because something, there's a field extension that has degree, not a power of 2. A lot of cool math that goes into it. Alright, that's what I got. What do you all got for me?
You've heard my issues this morning.
I did.
When I was complaining about the test problems I wasn't able to solve.
Number 1, I haven't heard about any others.
The test problem I wasn't able to solve then.
Oh, okay.
I would just look at it, but it is designed like number 1's the hard one.
That's what it looks like.
A little bit easier, right?
Like number 1's a hard one, but if you think so, sure.
Well, I don't know, wasn't it your thesis, like, the Galois theory?
No. Well, I mean, it was abstract algebra. I'll tell you, so my thesis was representation theory. Basically, getting into things we haven't talked about in this class called modules and comodules,
Oh.
which,
I have
Abby talked about those, didn't she?
She
I understood about 1/4 of what she said, and I probably understand more of it now, but I don't remember it well enough.
Yeah. Abby sent me this crazy representation theory paper like a couple weeks ago that apparently she and her research group wrote. That like I didn't understand more than 10% of. Abby Price doing good math now.
Is it good math or is it evil math?
I don't know, I didn't understand it, so I'm gonna say
It's just chaotic.
chaotic math. Yes, knowing her.
It's off the break, you get the
Yeah, no, my thesis was in looking at actually sort of these polynomials and multiple variables, except I did it over the integers, where I basically said, hey, suppose you take the look at all the different representations of this thing under this certain type of structure, and turns out they form a ring called the green ring, a representation ring, named after Sandy Green. By the way,
Wait, is that the same one in physics?
no, that's not. That's a different Green from say Green's theorem.
I was about to say,
I was like, wait, I
This is a
don't know that
green.
name before.
This is a Green whose name I haven't heard in any context outside representation theory. But basically, my thesis was looking at, hey, you've got this class of representations. They form a ring. I showed that that ring was isomorphic to a polynomial ring over the integers mod a really weird quotient thing structure.
Isn't that how you prove the fundamental theorem of finitely generated abelian groups?
There's a lot of ways you can prove. You can. There's a lot of ways you can prove the fundamental theorem of finitely generated abelian groups. Gag for those of you who had me in the fall.
Oh.
Uh,
I remember, good,
we use that. We called it that a lot. Yeah,
You
yeah,
don't
that's
have to say the whole
yeah.
thing.
yeah.
Yeah.
Representation theory is basically a way of saying this problem in abstract algebra is really hard. I don't know how to do it. I just want to solve it with matrices instead, or nice simpler things. Yeah, I taught a topics course a few years ago in representation theory. None of you were there.
Even if that was while I was here, there's a baby math student.
Actually, when was that? That was 3 years ago, so you would have been a freshman.
Little baby math student.
Would have been different.
That was the only other topics course I've taught to this point. That one had 3 students.
And now you're just the guy.
No. Yeah, now I have 13, and now I'm gonna have 20 in the fall. Oh my gosh.
And me, if I get to be in this area.
Yeah, and oh gosh.
I'll be in the back and I'll keep my mouth shut, but.
But yeah, I should say some inspirational words to wrap up this semester.
another joke, no, I'm just kidding.
All right, I got one for you.
Do you prefer teaching 3 students or this many?
Yeah, hold on, let me tell my joke first.
It's us 3.
Parker,
Yes.
that was a joke.
You killed him.
Good. Sorry, Jonah, what were you asking?
Do you prefer teaching 3 students or this class?
Those 3 students were a pretty rambunctious group.
Did you see this class for one moment?
This was much more so, yes.
Have you had a crazier class than us?
No. Well,
Not even his section of
I take that-
algebra last
I take that back. My first year when I was TAing Chinese as a sophomore in undergrad, that was a pretty crazy class. That was the time I was that was my first teaching experience. That was the time when, teaching stories. I have a lot of teaching stories for those of you who are taking my course in the fall. But here's one. TAing my first Chinese class, all my students told me one day they wanted to show up to class drunk. And I said, okay, sure, whatever. And then that happened to be the day that the professor came and sat in on my class to observe my TA performance.
Wait, they just all showed up drunk?
Yeah.
Well, they just
like half of them did. This was a 7 p.m. class, I should note.
Oh.
That's a little more understandable.
I was like,
It's like 11 a.m. There's day drinking.
The professor thought it was hilarious.
9 a.m. That's a bit different. Yeah.
Like,
What was more rambunctious, the representation in the class or our section of abstract last semester?
per capita or like total level of rambunctiousness? I mean, probably your abstract class.
The per capita can be pretty small for, what was it, 20 people, 24 people? To out rambunctious 3 people.
Yes.
Oh wait, that was the other section.
There's like a section, yeah, there's
Was it the other section?
Wait.
section was
You-
No, I think you were.
you were in the smaller one.
Okay.
Wait,
Yeah.
Look at that.
No, I
You were in the bigger one.
Wait.
oh
Yes,
yeah,
I
because that was in the later one.
Yeah, you sat in that, I remember you
I
sat in that
played
corner
And
back then.
I
What?
You
Well,
were,
I
yeah, you were
learned-
like over there.
Yeah.
I've learned over the
I
course
feel
of this
like I was-
semester, the way you write on the board, it's easier to see from this side of the class.
Fair. Oh, yeah.
And that's why I'm over here.
Yeah, y'all have anything in abstract algebra related you'd like to talk about stuff? Technically, we still have like 40 minutes.
We have a few minutes.
How does this all relate to the Rubik's Cube?
Yeah.
I saw a visual.
Galois theory specifically?
Yeah, well, I'm kind of curious about the Galois theory. Is there any relation? Because I know, like, isn't Rubik's Cube related to a subgroup of like S40? So
Yeah, I was gonna say Galois theory specifically. I'm not sure, but like you could like use abstract algebra to solve the Rubik's cube with like something called group actions.
Oh, I've heard about those.
Whoa.
Oh, y'all have, oh, we didn't do this in 410, but group actions are a lot of fun. It's basically, you have some set S, and you define a function that takes in some element in a group, and whatever element in your set S, and it spits out an element in that set S.
What is this GX?
That's a Cartesian product. It's basically, so basically, you could define like, you could have like S be like a like a configuration of the Rubik's cube,
Oh, that's like a.
and have like R,
Like a matrix transformation?
yeah, and have like phi of R,
Oh, okay.
configuration of Rubik's cube be a configuration of Rubik's cube where you've rotated the top level by 90 degrees,
Oh, that's
or you've rotated one of the
sides.
vertical side column,
Faces?
faces. Let's go with that by 90 degrees in a certain direction. You could have like talk about like how are ways that you could use ideas from like D4 or like the symmetric group to act on the faces of a Rubik's cube.
Yeah.
And there's a lot of cool results you could talk about, like in order to solve a Rubik's cube, what are the, sort of the sequences of elements in D4 that would cause that to happen from certain states.
So could you find like the quickest solution to a Rubik's Cube?
I mean,
Or would you
In
just
theory.
be able to find
I mean,
a
there-
solution?
that is like a competition category, so there's somehow people.
Yeah, there's like ways of doing it in theory. In practice, that's a very
Well, yes,
Big
practice is
Yeah,
question.
It kind of reminds me of just finding the quartic function.
another way, Matthew, that Rich shows up is Sudokus.
Oh.
Solving Sudokus, you could do a lot of like group action.
I feel like Sudoku is kind of like graph theory with it.
I feel like most
That is
puzzles.
too.
I feel like most puzzles this sort of falls under, really, like a lot of those sorts of puzzles.
There's some fun stuff you can do with Cayley tables and Rubik's cubes.
Oh.
When they do God's number and they're trying to find like the like just in general like oh like every Rubik's Cube, like now they know because they ran through Google's computers like 20 moves or less for me to solve. But like how did researchers do it when they got it down from like 34 to like 32 to like 30? Like how do they? Is there do you know like any of that behind it when it comes to the abstract algebra? Or
No.
okay.
You have to know if the group of like that acts on states of the Rubik's cube. Obviously, it could be generated in 6 elements because like one term for each face could
Mhm.
be generated in 5. Feels like
Yeah.
it could be.
Yeah, I think you can. I wish this can do fewer than that.
But not if you have one of those Rubik's cubes that where like they have pictures on them and so the way the centers work.
Oh, I hate those.
No, those are right.
What?
Jonah, speak no more of such monstrosities. I'm pretty sure the answer to that is yes, Josh. I haven't looked at this in like a very long time.
If they have pictures of the centers.
Can you get fewer than 5 though? That's a more difficult
No,
question.
that's how they're rotated.
Oh, or the
But when you solve the
orientation
Rubik's cube, the
matters.
color in the middle can be in any direction. But,
Yeah, like
Scratching it.
I've seen these, Jonah, and they scare me.
It's like a Rubik's Cube where each face.
You want a
is
good
picture,
competition problem,
but then
or
it's
a hard
automatically
competition problem, I
orientation
should
that you
say.
solve it.
Wait, is
So-
it genuinely, is it genuinely harder? I always
Yes.
thought that
Oh,
those,
it is
that
objective.
they had
Well, because
made
the
those so
color,
that they
it's
weren't
not about the
harder.
color anymore. It's not about the color, Spider-Man. You know, it's about the, it's, now it's about the orientation, which you have to get right. So
Well, I wasn't sure if
even
you
about
just like took a
Turn it-
Rubik's Cube.
getting him in the
Jonah
right
Jameson for a
cycle.
second.
You realize how
Getting-
many of your bottom layer algorithms do not hold constant the orientation of the side?
Yes.
Mhm.
Yeah, that's
You know, side orientation. There are some cubes like that like, oh man.
Short answer to your question, Matthew, is I'm not quite sure how Galois theory specifically can be used. There likely are ways, but there's definitely a lot of like good group theory and using a lot of the ideas that happen to appear in this class along the way in order to do things like that.
Speaking of graph theory, is there any relation between Galois theory and the fact that K5 is non-planar?
What is K5?
The complete graph of 5 vertices. That's the
thing.
smallest complete graph that's not planar.
I don't know either.
I mean, that does seem like the sort of.
I was gonna say, I feel like the answer is yes, but I couldn't give you an obvious answer as to why.
He's just like, I don't get it.
Yeah.
What?
Oh no, say that.
But it's also been found that
What, like,
uh,
like what?
There's no way to reorient these vertices so that like these things, so that these edges don't cross them, each other.
have a
Oh,
subgraph
in the plane.
K5
Yeah, in the plane.
or a subgraph of
Okay, yeah.
K3.
Whereas with something like 4,
Which is the
Yeah.
bipartite.
like even though it looks like, oh no, that crosses itself, you could like rearrange vertices.
I
In a way that's like-
sense.
But the K5 thing, oh yeah.
I feel like we just think about it in 3D.
All I
It's
understand.
not has that subgraph.
Wait, what about, yeah, so you could just go higher dimensions, Dr. Gerstle, it's just that simple.
Oh well, if you do that,
What?
yes, it
Are all
becomes
of
much easier.
Work
all of
on
this
a
supposed to be
torus,
connecting?
yeah.
Oh yeah, so there's something not connected.
You're missing the
Yeah,
third and
lines
the fourth one
across,
are not
like,
connecting.
If you work on a torus, it's possible, probably. Maybe, I don't know.
Yeah.
What's on the
That's not
torus?
really
not. So, so
Like connecting 5 points without them overlapping?
I didn't hear the first half of that.
How do you say we prove things like the trisecting
Maybe.
angle or
What
whatever?
about a torus?
You
How
basically-
would those?
I don't know.
Sure, so constructability ideas. So the very, 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 very high level idea is showing that trisecting an angle corresponds to taking an extension of Q of degree 3. The only things you can actually do with the straight edge and compass correspond to field extensions that are degree 2 or powers of 2. 3 is not a power of 2,
Wait, so how does?
therefore it doesn't. Therefore you can't construct it.
So what's the Galois correspondence for origami?
Origami is not just using straight edge and compass constructions.
Yeah, but you can trisect an angle with origami.
You can.
Is there a, like, how would you do,
Uh,
how does?
but basically, you're using tools that don't apply to the body of theory that kind of relates to what Jonah was asking about. Like, you're not just with like the. I mean, I'm sure there are Galois correspondences to like what you can do using origami.
Yeah.
I'm pretty sure I've seen these guys back in graduate school at some point.
Yeah,
But
is there-
that's allowing for more degrees of freedom.
Yeah.
And if you allow for that, then the theorem that requires things to be a power of 2 no longer needs to be a power of 2.
Yeah.
And so it becomes possible using other techniques outside of origami. But just using straight edge and compass, it's impossible to trisect the angle.
Unless you use
Well, a marked compass,
Or
I mean, on a
marked-
straight edge.
Is there a way to generalize the degree it takes to construct any regular n-gon? Because I know that there are some n-gons that you can create like a decaheptagon or whatever, 17-gon. But what about the more exotic ones where it's like maybe 19-gon or something?
Ask Dr. Murphy.
Okay,
That's very much his bailiwick, more so than mine.
nice.
Like it.
Back to
I need to talk to you after class again, by the way.
Yes, yeah.
You're rich.
Back to Galois theory for a sec. When we first introduced the Galois group, We had one that was isomorphic to D4 and talked a little bit about the sort of geometric considerations, how you can basically draw a square with that specific example in the complex plane.
So was that like x to the fourth plus 1 or?
Yeah, something like that, because they were all like
I'm trying to remember which polynomial it was. We definitely did do a D4, yeah.
the roots were I think root of 2I times, or rather root 2 times.
Okay, so like x to the fourth minus 2 then.
Yeah, right. And you said something about you don't know the half of the geometric stuff yet. Is there anything anything else you might be able to share on the sort of geometric?
I do not remember what that was in context, what I said that in reference to.
Well, all I was saying was, you know, you can actually use the roots. You can construct a square with those roots in the complex plane, and all the automorphisms, all the cube automorphisms correspond to.
Oh, like rotations of that, or D4 things with that square.
Yeah.
Mhm.
Anyway, are there any other fun geometric things with Galois?
Yeah, just DN in general. Are you talking about like beyond just working with the dihedral group? Yeah, there's a lot of fun geometry. There's a lot of fun geometry to be done. And Dr. Murphy's really the one who's, I would say, main research focus is kind of looking at this algebraic geometry, just kind of a whole field in and of itself. So he'd be a good person to actually talk to about these things. That's something I was going to say. Galois theory in particular, yes, there are others. James.
So, what is a lead group?
It's a group that doesn't tell the truth.
That's what I'm gonna say.
And you, Dr. Gusto.
What are we looking at now?
You just
K5
solved
on the
it,
Taurus.
I solved it.
Oh, you're solving K5 on the Taurus? Oh yeah, dude, yep.
When I wanna solve K6.
Yeah, well, yeah, if you're forcing yourself to work on a non-planar surface, then suddenly you can have a lot more weird things like that happening.
Well, then Dr. Gabler seemed to imply that people don't find it all that interesting, but what?
It is, well, okay, so when Dr. Gabler say math professionals don't find it that interesting, that's not because there's not like fun math to do with it. It's either, that usually either means A, it's been solved in like generality and there's nothing more to do here, or B, people just haven't worked on it yet.
Yeah. Are you doing 6?
Yeah, I'm doing 6 now.
You won't be around for topology. You didn't take it last
No,
semester.
I'm
That's
taking
good to hear.
topology.
Say what?
Unfortunately.
Topology was a lot of fun.
I wish I could take topology.
Topology's a fun class. Especially when you break your ankle and you force another professor to teach your class for 2 weeks on very little notice.
Do you think you'll be teaching it in the fall next year, or do you think it'll be Dr. Murphy?
When topology's taught next, who's going to be teaching it? I would say probably me, Dr. Gabler, or Dr. Murphy.
Okay.
Not next year though. That's still like 2 years out.
Yeah, it's fall 25.
How is that a Taurus?
So it's a Taurus basically
Here,
just a looping
When you have the arrow in the top and the arrow at the bottom that match up with each other, that means you're identifying them with each other. So you're kind of folding one into the other.
Okay.
I think
Can you do it for
like
any
it
And then if you fold the sides together, you get a
on a Taurus?
yeah.
Is
Oh,
there
okay. Yeah, so
is
you're
there a
right.
square?
Is there a what?
It's
Topology,
topology,
because I just saw
paper
something
around.
Yeah. There's one that's could I tell you what they are? No. Oh man.
That's so
Yeah.
wild.
Non-trivial.
A flattened
Very
torus
non-trivial
is
question.
like a,
When you grab the surface.
a flattened torus
Nice.
is like a.
You treat.
Lydia, are you enjoying this conversation?
At least you were here.
She turned it off.
She's already.
Lydia, I need to have a conversation with you at some point too. See me after class.
What?
What are these?
Yeah,
How much
I don't know what it is.
Yeah.
See, I just found
Anyway, I was gonna make a joke about that. Thanks for ruining the joke, guys.
Like when you play Pac-Man and he
Oh,
walks
yeah.
off one side, this here's on the other side.
Alright, I'm ending the video here.
Bye, Lydia!
Bye, Lydia. You don't need to see what comes